Yes, good morning, doctor. Um, Good morning. This is a notebook. Uh, I'm developing it in Google Colab. Doctor, there are some videos which I sent you some 2 weeks back of the showing the slides of the PowerPoint presentation of the project, the contents, the literature review, the the introduction, literature review, and how I'm going to develop the models, the model training, the architecture, and the architecture and how the models will be trained, and how uh, I will apply the explainability. But now this is this is a notebook. It's a tentative notebook. I'm trying out things here and there, but this is so far what I've tried to come up with. This is the imported the data sets. These are the various libraries which I used. This data here, as you can see here, the columns are cumulative. So I had to scale them down to normalize these cumulative columns. I used the normalization formula, whereby I got the difference in the timing, last poll, and then the difference in the cumulative values. Then I divided them by 60 so that I convert the data here to rates. I converted it to rates because I want it reduced on the training time, training the machine learning algorithms, and also to provide useful information. That we can. So that, for example, the total, I had to convert this to rates, transmission of bytes. The data here has to be, I converted it to rates so that there is some meaningful kind of information, because data is transmitted in form of a given metric per unit time. So that's why. And also I converted them so that I can reduce on the training time, because some of these values are too huge. So this is the histogram, the distribution, the univariate data analysis, the EDA. For example, here from this histogram, there is a lesser number of VM instances ranging between 0 to 5 VM IDs between 0 to 5, and then the number of instances keep on increasing as the number of VM IDs increase. So as you can see here, the VMI, there is a greatest number of VM instances between IDs 5 and 7. Then we go to the KDE plots. These are KDE plots. I can KDE plots, for example, if I can analyze one of these. For example, the TX packet rate, the number of packets. This PX packet is the rate of transmission of packets, the rate at which packets are being transmitted on the network. So you can see here that as the number of instances increase here, there is a normal kind of the number of actually here there is a greater number of a greater number of instances that experienced non-compromised traffic, and then a few number of instances experienced an increase in the attack and attack data. So here, at least the VM instances are very few, but there is an increase in the rate of compromisation of the data there as these packets are being transmitted on the network. Still, from here, I can realize that there are some KDE plots that represent actually the same information. Actually, if I can see here, so the KDE plot for TX bytes, the number of packets transmitted, the number of bytes transmitted on the network, and the number of bytes, the number of packets, the rate at which the packets are being transmitted on the network, and the rate at which the packets are being transmitted on the network. So these KDE plots are the same. They are the same. Even this one, they are the same here. They represent almost the same information. So here filling in missing values. So I realized that this data set had some zeros. I had to replace those columns with a very negligible, a small value. I replaced them with a very small value that will not lead to the because once we have those zeros, the model will not learn well, especially in those columns with the zeros. I had to replace those zeros with a very small value in those columns. So this is the data set that has been replaced with this. This is the feature actually. This is the imputing. This is in the imputation stage. Then after imputing, replacing the zeros with a very small negligible value, I came up with this heat map. This heat map here shows the correlation of the various random variables using the Pearson correlation coefficient. So here there are some highly correlated values or random variables and those which are negatively correlated. For example, TX bytes, the number of bytes that are received on the network positively correlates with the rate at which the packets are received on the network. So there is high correlation. So and then there is a low correlation. This is the brick red here displays those variables that are highly they are highly correlating negatively. Then here I built this. I did some data split, dividing the data set into X and Y. Then I did the model, the data split into training and testing, 80% training and 20% testing. Then this is what I have after splitting. This is a splitted uh, uh, then after splitting, then I did what I did the dataset balance. I balanced. So here I balance the training set. I balance the training set. So after balancing the training set, I came up with this fit map here. This fit map is almost the same as the other one. There's no difference. Then I scaled the data using the minimax scaler. Then I built the feed-forward neural network. But as I don't know why it's beginning at 82. Actually, I'm thinking this mode, as doctor told me earlier one time, that is overfitting. I'm trying all the mechanisms that I can do to stop this overfitting aspect. Because the accuracy is too high. And this is the confusion matrix. Here, I'm invoking the explainability with the lime. Here I instantiated. I trained the black box fit for a neural network. Then after that, I had to convert the data set, the trained data, into a 2D array, because this lime explainer, the lime explainer accepts only the data which has been scaled to a two-dimensional array, because that's one of the parameters it takes. So also I also had to scale the test data to a 2D NumPy array. So because this explainer here, inserting the lime explainer accepts 2D dimensional array data sets. So after that, I ran this code here. I came up with these explanations, these ones. For the first, the 1, 2, 3 instances, these are the instances, the VM instances, 1, 2, 3, and these are the they represent normal data, not compromised. So from there, I generated what we call sharp waterfall plots. As you can see, the sharp waterfall interpretation plots, they help us identify the features that are most relevant for model prediction. And here, for example, this is a waterfall plot for instance 0. So the important feature is the last memory update. Then the second feature is TX packets. So these instances, they are not the same as these ones. I think I made a mistake here. They should be the same. So I have to change the index here. I have to change the what? I have to change the instances here so that they connect. So the second, the waterfall plot for the first instance, as you can see, a memory update, last memory update. It is the one of the important features that leads to that model prediction. So I also implemented a convolutional neural network, CNN. The performance is almost the same as the previous ones. And that's where I've so far stopped. But I'm trying all the means to come up with the, because now here I realize here there's some redundant data here, redundant data redundancy. So I have to delete one of the, I have to remove one of the columns because they represent almost the same data. For example, this and this, I'll have to remove one of the columns, and also even this one and this one, because I'm seeing here the graphs, the KDE plots are almost similar. So maybe the overfitting component will be eliminated once I remove those columns. And also, when I look at this city map here, there are some random variables that are highly correlated. So I have to remove some of like for example, memory usable and memory. This is let me see. Let me see. Highly correlated. For example, CPU time is highly correlating with the CPU. So I have to remove one of those columns. One of those columns, and also HUD request rate is highly correlating with the HUD bytes rate. So I think once I remove those columns, I will be eliminating the. I'll try to run again and see if the overfitting as component will be removed. So that's the end of my presentation about this notebook. Yeah, this is the tentative notebook, not the. I'm trying to test the things here and there and see how the thing runs. There's a video which I sent you showing the slides of the proposal. I sent you much more earlier. So I beg to stop here. Thanks for your listening. I beg to stop here. Thank you. Stop.